Today, we are diving into Microchip's RISC-V initiative, that is Mi-5, and how to simulate Mi-5 soft CPUs. If you are working with FPGAs and want to explore RISC-V processors, this video is for you. Let's get started. First, let's understand what Mi-5 actually is. Mi-5 represents Microchip's RISC-V initiative and it comes in two main flavors. Mi-5 soft CPUs, which are 32-bit RISC-V ISA compliant processors that you can implement directly on Microchip's FPGA families. These work on PolarFire, SmartFusion 2, RTG4, and Igloo 2 FPGAs, which gives you a flexibility in your hardware platform choice. Next, we have PolarFire SoC FPGAs, which features a powerful 5-core 64-bit RISC-V CPU. What really interesting here is the AMP mode support for mixed real-time and Linux operation, meaning you can run both real-time application and Linux simultaneously. Let's walk through the complete simulation flow. First, we will access Microchip GitHub repository to download the Mi-5 reference design. This gives us our foundational hardware structure. Next, we will import a bare metal software example into Soft Console, build it to generate the hex file containing our executable code. Then we will initialize the SRAM with this hex file, ensuring our processor boots with the correct program. Finally, we will configure our test bench environment and launch the simulation in ModelSim, where we can observe real-time execution and validate our design. This end-to-end transforms RISC-V code into actionable hardware verification. To get started with our Mi-5 project, we need the FPGA reference design and the bare metal software example. First, go to the GitHub web page of Mi-5 soft RISC-V processors. The link I will provide in the description of this video also. Here you can see different options of various FPGA boards. Since we are working on PolarFire SoC Discovery Kit, we will focus on this link. It contains a script that generates FPGA reference design and Flash Pro Express job file for the Discovery Kit. Below, you will find Mi-5 RV32 bare metal examples. This repository provides ready-to-use drivers and example projects, which will include our sample project we are using in this demo. Click the PolarFire SoC Discovery Kit link to download or clone the reference design. Similarly, click on Mi-5 RB32 bare metal example to access the example project. You can either press the code button, download zip, or copy the Git URL and use it. With these two repositories, you will have the FPGA reference design and the matching software example. This ensures everything is pre-configured for our simulation project. Before proceeding, make sure you have unzipped both the bare metal example zip file and the reference design zip file that you have downloaded in the previous step. Next, we will open Libro and run the tickle script located in the reference design folder. Click on Project, then select Execute Script and browse to the location of your reference design where you will find the tickle script. In the argument field, enter Mi-5 RV32 CFG1. Then click Run. This ensures that the generated reference design is configured for the Mi-5 processor with required subsystems. Familiarize yourself with the project structure, focusing on the processor subsystem and memory blocks. In the Smart Design canvas, double-click the Mi-5 RV32 component, open the configurator, and enable the trace interface. Right-click the component and click Update Instance, and then promote all trace pin to the top level. Open Soft Console and import the bare metal project into Workspace. Browse to the location of your Mi-5 bare metal library. There are many projects in the workspace. We will deselect all the projects and select only My5 SysTick Blinky, which we will use in this demo. Click on Finish. Click on Source Application main.c. Now browse to line 107 in the main.c. We configure the My5 system timer interrupt to fire every 10 microseconds, enabling a very fast simulation cycle. This interrupt triggers our LED toggling logic. Now, come to GPIO initialization. We initialize the core GPIO block to use a 32-bit APV interface and set all outputs initially to 0 so the LEDs are off at boot. Next, we have HAL enable interrupt. We globally enable interrupt for all My5 cores and especially enable local system level interrupts. Next, come to the function that is void SysTick handler. This interrupt handler does two things. It increments a counter to track how many interrupts occur. Second, it exhausts the lower 4 bit of a value which toggles the GPIO line connected to the 4 LEDs. For the simulation part, we will disable all the UART. Now go to project and build the project. After the successful build, you will see a My5RV32i debug folder. In this folder, you have two files, .hex file and .lst file. The hex file we will initialize into our SRAM. Open Libro. In your hardware design environment, find the SRAM module and open the memory initialization settings by double-clicking it. Click on Memory Initialization Settings and set the initialize RAM at power up and browse to the newly generated hex file. This step ensures the My5 CPU will load and execute the correct application during simulation. Click Generate Component and build the design hierarchy. Now we will create and configure test bench. In design hierarchy, select base design component, right click and choose create test bench with smart design. And name the test bench as base design underscore TB. Then click OK. Go to catalog, check the simulation mode box and expand clock and management. Drag the clock generator to the smart design canvas. Accept the default name. Set the clock period for clock generation to 20,000 picosecond, that is 50 megahertz. Click OK. Similarly, drag the recent generator. Before that, we can connect the clock to the reference clock of their base design. Accept the default setting of reset generator, click OK and connect it to user reset. On the output side of test bench, promote LED1 to LED4 as well as all the trace outputs to the top level. I will mark unused TDO and TX pins. On the input side, make connection as shown in the video. Now, generate the test bench and save the project. In the stimulus hierarchy, right-click base design underscore TB, select simulate pre-synthesis design and choose open interactively to open ModelSim. Start the simulation. In ModelSim, we will run simulation for 1 millisecond. Click on run. After 1 millisecond, you will have the waveform like this. Now, we will examine these waveforms. We will first examine trace underscore interrupt. Every few microseconds, the Mi-5 processor receives a machine timer interrupt, indicated by an internal signal trace interrupt going high. This is what causes the processor to temporarily pause its main loop and jump to the interrupt service routine that is SysTick underscore handler. Now let's break down what happens step by step. Right here, we see the signal trace underscore I adder, which represents the instruction address or program counter. At this moment, it holds the value of 80000D76. That means the Mi-5 processor is currently executing code from this location. Next, the trace underscore INSN signal shows the 32 binary instruction fetch from that address. The value 0000C10C indicates a store instruction, specifically a write to a memory mapped peripheral. Just after that, we observe APB initiator P adder line. It shows 7500000A0, which is the memory mapped address of the GPIO register. This confirms that the processor is targeting a core GPIO. Next, take a look at APB initiator P write. It is high, indicating that this is a write transaction and not a read. Simultaneously, GPIO out changes to 0 cross F, which means all 4 GPIO are being driven higher. As a result, you can see LED 1 to LED 4 are turned on. A moment later, this entire sequence repeats. The same instruction address and the opcode execute again. The same GPIO address is written to, but this time GPIO out goes to 0 cross 0 and all full LEDs are turned off. This toggling pattern between 0 cross F and 0 cross 0 repeated with each interrupt is what creates the LED blinking effect in simulation. Thank you and stay tuned for more interesting videos on FPGA like this.